Okay, good day everyone. Welcome to Emerging Private Tutors. This is Mr Sithole. So today we are continuing on momentum. We're just finishing momentum. Remember, on our first lesson, we have covered the definition of momentum. We say the product of mass and velocity, and an object. Okay, and an object to have momentum, it must have mass and it must be in motion. It must be moving. And we also covered Newton's second law in terms of momentum. So, and change in momentum as well. So, and change in momentum due to your the velocity. So today we're going to look into impulse, the impulse, and from there we'll also look into the last part of conservation of what momentum. Okay, so let's get to work and see what's going on here. Okay. Okay, so here we are talking of impulse. Okay, and we are saying, remember we said in your Newton's second law, we said F net is equal to what? F net, which is a force that is exerted on the object, is equal to change in momentum over change in time. Okay, over change in time. But now, look what we have now. What we have when we're talking of impulse is actually a product of resultant or a net force acting on an object, and the time the resultant force acts on the object. So, impulse, when we're talking of impulse, we are saying it's equal to the F net, product of F net and time that are on the object. And if you can see what we have there, F net times time. And what do we have here if we are to move that time there? We'll have F net times change in time equal to change in momentum. So basically, impulse is change in momentum. So when you ask to find impulse, they're actually asking for a change in momentum. Okay, so there is no big deal here. But now understand something here. We are going to have what called impulse, since it's going to be F net times what? Times what is it? Times time as well. You can have two units here. So if it is depth of change in momentum, you know that it's kg meters per second. Okay. What if it is F net times time? It's going to be Newton second. It's going to be Newton second. Okay. So therefore, 1 Newton second is equal to 1 gram per kg meters per second. Okay, that's what we have there. So these two are equal. So you must understand also that since impulse is actually product of F net and time, your impulse again becomes a vector as well. So impulse is therefore a vector because of the force that we have. You know that force is also what? Force is a vector quantity. So here it's also a vector quantity. So always remember to include the magnitude and what? And direction. Always remember that. That's what you must remember here. Okay. So let's see what we have here. So what we have here is that this is what called impulse momentum theorem. Impulse momentum theorem. So here what we have here, we are saying, if we are saying F net change in time, so it's called impulse momentum theorem. Sorry, my things are a bit splashed up. All right, impulse momentum theorem, you're saying it's equal to m times change in v, because remember, m times v, change in v is your change in what? Change in momentum. So that's what we have there. So therefore your impulse is equal to change in momentum. Okay, so let's have maybe a few examples that we can work on. Let's have a few examples that we can work on. See what we have there. So look what we have here. So we are saying a cricket ball weighing 156 grams is moving at 50 kilometers per hour towards the batsman. It is hit by the batsman back towards the bowler at 86 kilometers per hour. Calculate the ball's impulse, and the second question we look into it. So what did I say last time? Remember, you need to write down what's given to you and what is being asked of you. Okay, so first of all here, what is given to us here? So we are saying for the ball, the one that we have here, what is the mass? Mass is equal to what? Mass is equal to 156 grams. And what must we do? We must divide it by 1,000. Always remember, because your mass must be in kg. Okay, that's the measuring unit. Okay, so let's calculate here and see. Okay, say 156 divided by 1,000. Okay, what do we have here? 0.156 kg. Okay, that's our mass. And what do we have again here in terms of what you call in terms of your velocity? We have initial velocity here. What is the initial velocity here? V initial is equals to 54 kilometers per hour. What did we say again here? We need to convert this because we want our unit as meters per second. What must we do again? We must say 54 times 1,000, which is in terms of meters, 1,000 meters in 1 kilometer, over 3,600 seconds. Okay, over 300 what you call 3,600 seconds in an hour. Okay, because in 1 hour you have 3,600 seconds. So what do we get here? We say 54, okay, times what do we have there? 1,000. Okay, let's see, 3,600. Okay. Yeah, what do we get here? We get 15 meters per second. Okay, 15 meters per second. Now let's check here. We are told that it is hit by the batsman towards the bowler. Now what we have here is that at 36. So V initial, V final is gonna be what? It's going to be 36 kilometers per hour. What must we do again? 36 times 1,000, okay, over 3,600. What do we get there? Let me see here. 36. What do we get? We get 10 meters per 10 meters per second. Okay. Okay. Now, but here let's see what we have there. We are told that is towards here is toward the batsman. So let's choose here positive is towards batsman. Okay, so that's what we have here. So here we are saying that's our positive side. So here it means that we are going to say this one, because that's a V initial, it's positive. Okay, so here we're going to say this is positive, and here now is toward the bowler, so it means that it's gonna be negative. Yeah, it's gonna be negative. Yeah, it's negative, it's no longer positive here. So our final velocity here is what we call negative 10 meters per second. Okay, now what else do we need here? I think we have everything that we want here. Now how do we calculate impulse? Ball's impulse? First, you must calculate change in momentum. Okay, change in what? Change in momentum. So what do we do when we say change in momentum? Change in momentum, we know that it's going to be equal to P final minus P initial. Final momentum minus P initial, which is equal to M, since we have got the same M, the same, V final minus V initial, which is equal to, what do we have here? 0.156. Okay, in brackets we have what? What is the final velocity? Is negative 10 minus what is the initial? Is 15. Okay, that's what we have there. Then what do we get there? We're going to say, let's calculate here and see 0 156, okay, bracket, negative 10 minus 15. What do we get there? We get negative 3,9. Negative 3,9 what? Negative 3,9 kg meters per second. But now look, we've got a negative here. So it means that it's actually moving away from the polar. So it's towards the what? Towards the polar. So what are we going to say now? We're going to say the change in momentum here is going to be positive 3,9 kg meters per second towards the polar. Okay, that's what we get there. Then so that's your what you call that's your answer there in terms of momentum. So now you know that impulse is equal to change in momentum. So therefore our impulse here is equal to 3,9 kg meters per second towards the polar. Okay, that's what we get there. Now the next question is saying calculate the average force exerted by the bed if the ball is in contact with the bed for 0,13. Okay, if the ball is in contact. Okay, now this is our time now. So what are we given? We are given change in time. Change in time is equal to what? Is equal to 0,13. And what else do we have as well? We have our momentum, change in what? Change in momentum. We have impulse, sorry. We have impulse. Now, impulse, which is equal to 3,9 kg meters per second. That's what we have there. Now, so what are we going to do now? We're going to say, remember, it's towards the polar. Now we're going to say now our F net, we know that F net times change in time is equal to your impulse. That's what we have learned. Now we have impulse there. We have what we want F net. F net is equal to, which is negative 3,9 divided by your time there is 0,13. Okay, so let's say this one divided by 0,13. Okay, what do we get here? We get negative 30 Newton. So here, why is it negative? Because it's towards the bed. Remember, 30 Newton towards the polar. Okay, that's what we have there. So that's what you must understand here when you're talking of vertical. So you must write first, you must choose your positive side first. You choose your positive side, you convert your mass before you do anything. Convert your mass, make sure that your mass is in kg. You also make sure that your velocity is in meters per second, like what we did here. Okay. So let's move on to the next part here. So the next part here is gonna be conservation of momentum. Conservation of what? Momentum. So here we are now looking at the conservation of momentum, and we have terms that we need to understand here. Terms that we need to understand, like these terms here. These are the important terms that you need to understand what called for your exams. Okay. Now, what is a system? So a system is any what called physical space. Okay, physical space that we are considering when investigating or solving a particular problem. So here, any particular what you call space that we are using to carry out our experiment. Now here we have isolated system. So isolated system, in this system here, the net force on the system is 0. So there is no other external force here. So there is no other external force here in this case. There is no other external force like frictional force. So it's like you're moving, let's say it's a car that you're pushing or sliding down maybe what can I say? A smooth flow. Okay, there is no friction. So on that smooth flow, we are seeing that there is no external force just sliding down on it. There is no isolated. There is no, that's an isolated system. There is no external force. Now, what is internal force? Internal force is a force that objects exert on each other within a system, like contact force between colliding cars, okay, or also a gravitational force in terms of weight. So in terms of weight, it's actually internal force that we have, okay, that all the objects have, all objects with mass have, okay, they do have gravitational force. Now, external force, this is an outside force now acting on an object within a system. So here we are saying that this is my phone here, and the state is sitting there. There is no other force that is acting on it, and it's stationary there. So now when I try to push it now, that's what you call an applied force. Okay, and when I'm pushing it again, there is another force also that is going opposite motion, which is your frictional force. So those are outside, what you call outside force. Then if you are to see that, yes, we know that free fall, when I'm saying free fall, we'll talk about that when we talk about, but when we talk about free fall, we're saying all objects, they actually have what was same acceleration due to gravity. So it means that if you are to drop in the absence of air resistance, if you are to drop this phone and a car from a same height, they will reach the ground same time, even a feather. If you drop them, what you call in the absence of air resistance, they will reach, and other forces, they will reach the ground, what you call with at the same time. So here we are saying here air resistance is also another external force. So we are saying if we don't have this, that's what. So these are called external force. So external force also is also what you call air resistance. Now let's look into law of conservation of momentum. What does it say? Now, the total linear momentum in an inelastic system is constant in magnitude and direction. So you must know that total momentum in an inelastic system is constant, doesn't change. So what do we mean by that? We are saying P initial, total momentum, P initial, what you call is equal to your final momentum. So after collision, remember, if two objects are to collide together, they actually what you call the object that is moving, maybe it's moving this direction, and another maybe these are snooker balls, okay? So remember this one, maybe the white ball, you're moving, you hit the white ball, and this one is approaching maybe a black ball, okay? A black ball is stationary, okay? Now, when a white ball approaches what you call hit the black ball, this will come to rest, and the black ball will continue with the same, will reach the same what you call same velocity as what you call as the first ball. So we are saying in that way momentum is conserved, because when this one comes to rest, it means that your final velocity now for this ball will be 0, and final velocity for this, initial velocity for this was 0, but final velocity will be something else, which is actually equal to the first what we call initial velocity. So you find that that's what we need to understand here when I'm saying momentum is conserved, because the energy is passed on to another what you call, it's passed on, it's transferred to another object, and that object carries on with the same velocity. And we are saying in that case the initial momentum will be equal to what you call final momentum. Okay, so here what do we mean by this? Let's say here we are saying object A and B. So this is B, this is 1, this is 2. Okay, so we are saying mv summation of P initial is equal to summation of P total, P final. Okay, now here summation means sum of, this means sum of. So when you see this sign here, it means sum of, so it's total. Then we're saying here we're going to say, all right, for this ball and this ball initially, we are saying M1 V1 initial plus M2 V2 initial is equal to M1 V2 final plus M2 V. So here it's gonna be V1 as well, V1 final. Okay, so that's what you call the V2. Sorry, V2 final. So we are saying here, if we are to add the momentum for the first ball and the momentum or initial momentum for the second ball is equal to final momentum for the first ball plus final momentum for the second ball. That's what we are talking about here. Okay, that's what we call conservation of what momentum. Let's see if we can have some what we call different scenarios here. So here, this is the first scenario here. When objects collide and then move away from each other, that's what normally happens, like snooker balls, like what I was giving an example. So this is the first scenario that you can have in terms of momentum, where the objects first they will separate, and again here after collision they do separate. Let's see the second scenario here. What we have here, when objects collide and remain attached, okay, to each other and move as a unit of after collision. So like if cars maybe collide, after colliding, what happens? They attach to each other and move together. Or you can fire a bullet, okay? So let's say it's a bullet here. What you call it? This is a stationary block, okay? And we've got a bullet here, okay? The bullet here that is moving towards towards the block, okay? Towards the block there. Then what happens after that? We see that the block and the bullet are now moving together because the bullet now is inside the is inside the block. So here we are now having mass of the block and the they are now moving together here. But before collision, they are separate. So how do you represent that scenario? We are saying it's gonna be M1 V1 initial plus, because they are separate here, plus M2 V2 initial is equal to, but now remember they are now together, so it means that they have same velocity, they are moving the same speed. So V here is gonna be fine, it's gonna be it's gonna be the same. So here V final is the same, so we're going to say V final here for everything is the same, plus M1 plus M2. That's what we have here. That's what we have. So we just add them. So this is the formula that so you must first see what is the scenario, and if you see that the objects at first they were separate and now they are together, it means that you need to come up with a formula like that, okay? Because they are moving with the same velocity, but the masses are always different, okay? Now, what happens also in the case of what you call the scenario here during explosion? What happens during explosion? Let's say you're firing a gun. You're firing a gun. So this is the gun here. This is a gun here. I don't know what's going to happen now here. So we'll just say it's a pistol like that, okay? Okay. So here, this is a gun, and we have a bullet here. So what you must understand here, when you fire the gun, I think you've seen that when you fire a gun, there is there is a force also exerted to the gun. That's why you see the gun, especially if you're firing AK-47, it tends to move back. It tends to move back. What is that? It means that the bullet also is exerting force towards towards the bullet, the gun, and the gun as well exerted force also towards towards the bullet. Okay, so what do we have there? Okay, so here let's see what we are saying here, what we're talking about here. What is it? We can see that when you fire a gun, initially, both of them they are stationary. So what do we have here? We are saying M1, the V. So this is a gun. This is a what? A bullet. Okay. So we are saying the V initial for the bullet, for the gun, is equal to 0, and the V initial for the bullet as well is equal to what? Is equal to 0. That's what we have here, because they are stationary from the beginning, but now finally they will all move. Okay, so after firing, you actually see that what is it? A gunfire here. What actually you see that initially they are not moving, but finally they will move. Now here, so it means that M1 V1 initial plus M1 m2 v2 initial is going to be equal to m m1 v1 final plus m2 v2 final. But understand something here. This will give you 0 because both of these are zeros. Okay, because they are both 0. So this one will give you 0, which is going to be like that. So what it means here, it means that your general formula here will be this one is equal to 0. Okay, so general formula here in that case will be m1 v1 final plus m2 v2 final equal to 0. That's what we have. That's what you just have to think of whenever you're given a scenario of explosion. Okay, let's see what's our next. Okay, I've just seen something here that I forgot to indicate here. So here, in terms of a gunfire, in this scenario, in terms of explosion, in terms of a gunfire, this is what you have. Okay, this is what we have here. But also imagine we can also have a scenario where we have what is it, a car and its trailer, okay, separate, okay, maybe after collision or something like that. Okay, so after an explosion, or maybe you can just separate along the way. So we are saying here, initially here we have m1, because remember they will be moving together, because they will be having same velocity. So maybe a car and trailer separate on explosion. So when these two separate, mean that initially the v initial for both is the same. So what it means there, it means there's going to be m1 plus m2, because they have different masses, but v initial is the same, is equal to what, m1 v1 final plus m2 v2 final as well. So here is, you can see that it's a reverse of that. Okay, it's a reverse of that. So here they are saying the two move together after colliding, but here the two move together before the collision, before the explosion. Okay, that's what we have. So now let's move on to different types of collision. Different types of collision. So we have unique two different types of collision here: elastic collision and inelastic collision. So what we understand when we talk of elastic collision. So elastic collision is where your total momentum, okay, and kinetic energy is conserved after collision. So after the collision, both of these, or during the collision, total kinetic energy and total momentum is actually conserved. Remember, the law of conservation of momentum, nothing can break it, okay, because momentum is always conserved. But in this case here, kinetic energy can be conserved or cannot be conserved. So here in this case, elastic collision involves what called objects that actually doesn't lose their kinetic energy. Now remember, energy cannot be lost, or energy cannot be created, isn't it? So it can only be transformed from one form to another form. So it cannot be lost. Now here, so what do we have here? We are saying elastic energy, like I said, momentum and kinetic energy is conserved. This is our equation here. This is our equations here. So both of them, they are actually conserved. Okay. Now, but let's check with an example here. So, snooker balls. Let's give an example of snooker balls. So remember, after colliding, the snooker balls separate, isn't it? That's what happens on elastic collision. So all elastic collisions, they are after collision, objects move separate ways, isn't it? So objects separate after collision. So they don't move together. That's what you might understand here. So here in this case here, the two equation that will satisfy the elastic collision will be equal to, so for momentum will be equal EP final which is equals to m1 v1 final initial, sorry, plus m2 v2 initial is equal to m1 sorry v1 final plus m2 v2 final. Okay, that's what satisfies the momentum. Then also in terms of kinetic energy, remember initially is equal to sum of your final what you call kinetic energy. What do we mean by that? So we're going to say half m1 v1 initial squared plus half m2 v2 initial squared is equal to what? Is equal to half m1 v1 final squared here plus half m1 m2 sorry v2 squared final. And remember, your kinetic energy is calculated as half mv squared. M is your mass in kg, v is your velocity in meters per second. So this is velocity. Okay, so you must always, you do the same, you need to convert if there's need for conversion. Okay, so you need to convert if there's need. Okay, so in this case here, your units must always remain what called meters per seconds and kgs. Okay, in terms of weight. Now let's move on to inelastic collision. Now what happens now to inelastic collision here? Inelastic collision is where total momentum is conserved, but total kinetic energy is not conserved in this case. Now what happens now? So kinetic energy is transformed to other forms of energy like heat energy and sound energy. So this is a good example here. When two cars collide and after collision, they move together. And have you ever noticed that when two cars collide, okay, and what call there is deformation of the body. So there is deformation of the body of what call of the object. Okay, so that's a car body. So once you have deformation, that deformation, you also see that after the collision there, you also see that on the point of collision there is two, it's what called it's heat, it's hot, isn't it? It's hot. So it means that is remember that energy and that sound that you hear after the collision, that sound, isn't it? And where is that sound? Where that sound coming from? It's coming from the kinetic energy, which is the movement energy. It's coming from kinetic energy. So here, kinetic energy is converted to other forms. So on collision, kinetic energy is no longer the same after collision because it's now it's reduced in fact. So it's transformed to other forms like heat that you can actually feel, and also also sound that you actually hear from a distance, that oh, the two cars have collided there. So what does this mean here? It means that here we are going to say, all right, here initial the momentum is fine. Momentum is fine. It's still satisfied here. M1 V1 initial plus M2 V2 initial. So also is equal to M1 V1 final plus M2 V2 final. So these are actually, there's no doubt they're actually equal. Okay, it's conserved here, like I said. But in terms of what kinetic energy is not conserved. These two are not equal. Total initial kinetic energy is not equal to total final kinetic energy. Now let's consider an example here. Consider the collision of two cars. Car one is at rest. Remember, if it is at rest, what happens? Remember what I've said in our first part of momentum. Then car two is moving at a speed of 2 meters per second to the left. Okay, both cars are each have a mass of 500 kg, equal mass. The cars collide inelastically. Oh, they've told you here, inelastically, and stick together. Now, what is the resulting what call velocity of what call of the resulting mass of metal? So now, what we need to know here? What is given to us here? What is given to us? So we know that car one. We're going to do the car one here. The first car here. What is given to us there? It means that what is given to us there is that what is it? It's initial velocity v initial is equal to 0. It's at rest. Okay. Now, car 2 is moving at what called that, and we don't know the V2. V2 we are going to do. Then mass here is 500 kg. Now here, remember what do we have here? We're going to say car 2 is moving at a speed of this to the left. To the left. So we can say, all right, let's consider left positive. So let's consider left positive. This is 0, initial is 0. So V our final, our for car B, for car 2, what do we have here? We have V initial is equal to what? V initial is going to be equal to what you call 2 meters is positive, 2 meters per second. Then what is our mass? Our mass is still remain 500 kg. So this actually before collision. But after collision, we find that after collision, what do we have here? After collision here, we find that this is before. What about after? After here, we find that here, the V final is the same for both cars because they move together. Because they move together, they stick together and move together. So their V final should be the same. And what do we have here? What do we have here when we have what called the mass? So it means that the mass here is going to be equal to 500 plus 500, which is equal to 1000 kg. That's what we have there. So let's work out and see. We are told that this is the scenario, they collide after what called they stick to each other. So we know that if they stick to each other, our V final is the same. So what we do, we say M1 V1, okay, initial plus M2 V2 initial is equals to V final M1 plus M2, because we know that mass might be different, but here we are saying the velocity is the same, so we factor out V there. Now what are we going to get here? M1 mass 1 is 500. Okay, what is V initial for M1 is 0. Okay, plus what is your M2 here? M2 is 500. Okay, what is your velocity here is 2 is equal to, what is the velocity? Velocity is the one in question because we want the velocity here. It's the one in question. Now, what do we have here? We have M1 plus M2. Remember, it's 1000 kg. Now, what do we do now? We have this. This one is going to be 0. So V final here, if we are to divide both sides here, so it means that 1000 is equals to V final, which we need to divide both sides. So V final here should be equal to 1000 over 1000, which is equal to what? Which is equal to 1000, which is equals to 1. Okay, which is equals to 1 meters per second. But remember, it's positive 1. So what does it mean? It means that it's actually still moving to the left. Okay, so it means that it's 1 meters per second vertical to the left. That's what we have here. So you need to put the direction here to say direction. My direction should be positive when you are going to the left. Okay, so that's what we have here. That's what we're talking about. So this is basically the end of our the momentum. Okay, so you must first what you call attend that first lesson for the first momentum, for momentum 1. Okay, that involves what is it? All the all right. So I think you all understood what you need to understand about momentum all in all. So what you need to understand about momentum is about converting whatever you're given to kgs in terms of mass, to meters per second in terms of velocity, and also you must remember to know, to determine the positive side, okay, the positive direction. What is my positive direction? So that whenever you're working, whenever you're presenting whatever is given to you, V final, V initial, you must know which one should I say positive, which one should I say negative. Okay, that's what you must always remember. That's the tricky part only that you need to remember. So make sure that you actually take serious what we call the positive, the signs. The signs are very much important, and the direction is very much also important. Okay, so until next time, thank you so much. Have a good day.